3.3 Fluid dynamics. Overall flow dynamics. System 1. A definite mass of fluid. A particle interacts with surroundings at boundaries. 2. A definite volume in space through which fluid flows. Variables. 1. Thermodynamic state variables. E, S, V, T, P. 2. Mechanical state variables. Velocity, kinetic energy equals 1/2 mv squared. Pressure P. Note that pressure plays both a thermodynamic and mechanical role. 3. Specific values. E, S, V equals 1 divided by rho. U squared divided by 2. Changes of state. 1. Thermodynamics equation of state. Specifies fluid. 2. Energy equation. Includes U squared divided by 2. A generalization of the 1st law. 3. Momentum equation. 4. Continuity equation. Reference system. 1. Lagrangian system. Follows all of the fluid particles x equals x of t, x sub 0. 2. Eulerian system. Specifies a velocity field u of x, t, where a particle in the field at x, t moves with the instantaneous velocity given by the velocity field at that point. Note, for steady flow the velocity field is no longer time-dependent. U equals u of x, while such a simplification does not occur in the Lagrangian framework.
3.3.1 Quasi-1D flow. Quasi-1D flow occurs with flow in a channel, tube, or nozzle, where cross-sectional area depends on 1D only, e.g., with cross-sectional area A of x, for example. Quasi-1D flow is designed to exist in a jet engine nozzle, for example, and requires continuity and momentum flux, etc. Equations specialized to quasi-1D flow. Even with specialization to quasi-1D flow, the description can quickly devolve to requiring a computer to handle computations. The focus here will be to carry through the analysis to the realization of a new feature akin to the emergence of a phase transition as seen in the PV curves mentioned in Secretary X, where here that new feature is shock formation in the flow. Shocks are a remarkable and ubiquitous feature of quasi-1D flow, such as jet engine nozzle flow, an example of one of the emergent structural aspects of statistical mechanics that is discussed at length in Book 6.
Using the notation introduced above, let's consider continuity, quasi-1D with only xdim free. See equation 3-106. Thus, see equation 3-107. Conservation of mass then becomes, see equation 3-108. Now, even though the flow profiles clearly show A of x is not constant, u x, flow vectors not parallel, in the differential limit we can still take the fraction with numerator partial differential and denominator partial differential t times rho A times d vector x partial derivative of rho with respect to time A of x d vector x partial derivative of rho with respect to time dv. Thus, see equation 3-109.
The integral term is the time-dependent part, if present, while the boundary terms are the convective part of the flow. If there is steady flow, then we simply have. See equation 3-110. Quasi-1D continuity. Let's focus more specifically on continuity in the quasi-1D case. If steady flow we have from above. See the next equation, where we now assume rho UA is differentiable. If flow is non-steady, this generalizes to. See equation 3-111. If we compare to the equation z.1 for flow with unit cross-section. See the next equation. We see there is agreement. Quasi-1D Bernoulli, with incompressible flow.
If flow in a pipe is steady, then equation z.2 indicated the Bernoulli result. See equation 3-112. At this juncture, it is convenient to shift from the notation adopted by L&L to the notation of Liepmann and Rashko, where an extensive analysis of shock formation and dynamics is discussed. In what follows we will now reprise the fluid dynamics of sector 3.1 for quasi-1D, in the notation of R&L, and then extend to describe shock formation. This is done to demonstrate the existence of such phenomenon, so more complex dynamical aspects are left to the complete exposition given in R&L. In the notation of Liepmann and Rashko we have for enthalpy H naught W, and for flow velocity we use U naught V, and external heat added, if present, is denoted by Q. Thus, For steady flow that is adiabatic, Q equals 0.
See equation 3-113. If external heat Q is added. See equation 3-114. Where U sub 2 is at the cross-section downstream, after heat added. Note the following definitions. Thermally perfect gas. A gas is thermally perfect if C sub P dt plus U du equals 0. Calorically perfect gas. A thermally perfect gas where C sub P is constant. C sub Pt plus 1/2 U squared equals constant.
Quasi-1D Euler and Bernoulli, with compressible flow. Previously we obtained for Euler's equation Z.3. See equation 3-115. And now specialized to quasi-1D, Q1D. See equation 3-116. For steady flow in Q1D we, thus, have. See equation 3-117. Thus, see equation 3-118. If incompressible, this simplifies to. See equation 3-119. As indicated previously. The previous discussion, however, was more focused on liquids, with typical examples presented, while here we are mainly focused on gas dynamics, for which compressible flow must be considered.
The Q1D momentum equation. Combining Ecn 3-116 and the continuity equation. See equation 3-120. If we integrate with respect to x between two cross-sectional areas A sub 1 and A sub 2. See equation 3-121. Some common definitions. Isentropic Q1D flow, adiabatic, non-viscous, non-conducting flow is isentropic. A perfect gas with isentropic flows satisfies. See equation 3-122. Compressibility. Compressibility of fluid flow is described by. See equation 3-123. Where is the speed of sound in the fluid? Using the above for a perfect isentropic gas in the form.
See equation 3-124. Mach number, m. The Mach number of the flow is a measure of speed in units of the speed of sound. See equation 3-125. If the flow speed has m is greater than 1, it is supersonic. If m is less than 1, it is subsonic. The area-velocity relation. Recall that ρ UA equals const period along streamline tube, or see equation 3-126.
For steady adiabatic flow. Recall that Euler's equation for steady flow was. See the next equation. Thus, see the next equation. Or, using the Mach number notation with the equals U divided by m. See equation 3-127. From the above form we can immediately ascertain the following. 1. If m equals 0, then decrease in area is proportional to increase in velocity. 2. If m is less than 0, subsonic, then as with m equals 0, except greater change for velocity. 3. If n is greater than 0, supersonic, then increase in area is proportional to increase in velocity. 4. If m equals 1, then must have dA equals 0, e.g., must be at throat in the flow tube, throat has dA equals 0. Near m equals 1, have extreme sensitivity to normal dA, if not 0. Flow at a throat.
There can be more than one throat constriction in a flow, but only one will be considered in the flow examples to follow. To have condition for throat dA equals 0, we must have either m equals 1 and du is not equal to 0 or m is not equal to 1 and du equals 0. Furthermore, this indicates a maximum velocity at the throat for subsonic flow, and a minimum velocity for supersonic flow. When m equals 1, sonic flow, let's denote other variables with an asterisk. Just as a thermal reservoir or asymptotic flow might be a useful reference, so too with the sonic flow variables at a throat. Since m equals u divided by a in general, we have u raised to the asterisk power equals a raised to the asterisk power. Let's now write flow relations with reference to reservoir values and the throat values. Consider the calorically perfect gas. C sub Pt plus 1/2 U squared equals const equals C sub Pt sub 0, where reference is first made to a reservoir at temperature T sub 0, where U equals 0, since we have a squared equals gamma RT.
See equation 3-128. The isentropic relations at the throat, with reference to the reservoir, then become. See equation 3-129. And see equation 3-130. For air we have gamma equals 1.40. Now let's specialize the above form to evaluation at the throat. See equation 3-131. For air, the fraction with numerator t raised to the asterisk power and denominator t sub 0 equals 0.833, the fraction with numerator p raised to the asterisk power and denominator p sub 0 equals 0.528, and the fraction with numerator rho raised to the asterisk power and denominator rho sub 0 equals 0.634. Note that a throat need not exist for the sonic value to be used as a reference.
According to the notation, m raised to the asterisk power equals 1 trivially, but it is convention to interpret. See equation 3-132, where it is understood that you need not be u raised to the asterisk power. Using this confusing convention we can then write. See equation 3-133, or inverting. See equation 3-134. Note the critical behavior that if m is less than 1, then m raised to the asterisk power is less than 1, and if m raised to the asterisk power is greater than 1, then m is greater than 1.